thing that has a cyano group on it, right? A nitrile cyano group, CN, C triple bonded to N, right there. And we're going to hydrolyze that. You can hydrolyze it in aqueous acid to a carboxyl group and an ammonium ion. In this case, we're actually going to get an ammonium ion, right? Not just, oh, a protonated amine, depending on what we've got, right? Because this nitrogen doesn't start with anything bonded to it except that carbon. And we're gonna break that triple bond, right? So, weirdly enough, this one actually forms NH4+, instead of just their specific example forming NH4+. Don't ask me why they make stupid examples. I don't know, but I don't like it, I'm against it. Let's see, protonation of the nitrogen atom gives a cation. So, protonate, okay, they're not going to show it, but protonation of this gives a cation that's going to give you an emitic acid. So, enol of an amide, it gives you an amide, but it's the enol version. And then tautomerism of that, ketoenol tautomerism, is going to give you an amide. So the amide can then be hydrolyzed to, or is then hydrolyzed to a carboxylic acid and an ammonium ion. So that's the first part. And it forms, where are we? Oh. I skipped. Amides can be hydrolyzed in aqueous acid, which we did. Right? Did we do this in aqueous acid? Yeah, we did this in acid when we did our mechanism. You can also do this in base. And now they give us an example that's not stupid. They put something on the nitrogen. So that's better. I'm not going to do this mechanism. It's on your slides. It's very similar to other attacking things, but you're more than welcome to come to office hours or my TA's office hours, or come bother me during their office hours or whatever, if you would like to see that mechanism, or go over any mechanism, because I love mechanisms. You cannot crush my mechanism enthusiasm. All right, where actually are we? Amides in aqueous base. Oh, okay. Okay, yeah. Amides of aqueous base, there's a mechanism for this. Hydrolysis of nitriles, I'm not gonna draw the mechanism for this, actually. That's nice. So basically, the steps without actual mechanism arrow pushing things, you're gonna protonate this, which is then going to have a positive charge here, and it's gonna go, hey, you know what? What if we don't do that? And it's going to break that double bond, and you're gonna have this. So that's gonna take its lone pair back because it would rather have a lone pair, and this guy's gonna go, wait, I'm electrophilic, and water is going to come in and go, don't worry, I can be a nucleophile, and then, deprotonate, get an enol version of an amide. Then you're gonna do ketoenol tautomerization to get your amide, and then you're going to do the amide hydrolysis that we already did in acid and know it in base. So if we have time after this, we'll do it, but come to office hours if you're gonna do that. Let's see. Hydrolysis of a cyano group in aqueous base. This is aqueous acid, so you can hydrolyze a nitrile in acid or base. In aqueous base, the steps are going to be, you're going to get a carboxylate anion, and ammonia. So not ammonium and a carboxylic acid, but literally the exact same thing, just, your pH has changed, so move the protons to where they make sense at a basic pH, and there you go. And then it's almost like you don't have to memorize two different things. It's just hydrolysis gives you this, and then acid or base, and do the charges. So the reaction is driven to completion by the acid-base reaction between the carboxylic acid and the base to form a carboxylate anion. So like, you end up forming your carboxylic acid, right? You get this guy, you're going to end up with water and heat. Yeah, so in the mechanism, just like in the basic mechanism, did we do the basic mechanism of, we did do the basic mechanism of amide, didn't we? Hydrolysis of amide. Did we do both? We totally did. And I just, no? I have a memory of like, so then at the end of your acid one, did I deprotonate? Where's the end of your, okay. Oh no, we did that, okay. Sorry, the mechanisms are all so similar, I can easily invent memories of teaching one, I guess. It's fine, I'm not suggestible. Okay, so when you do the mechanism for forming, for hydrolysis of an amide, so back in an amide, or at the end of hydrolysis of a nitrile, you're going to get an amide, or in the middle of hydrolysis of a nitrile, you're going to get an amide, then you're going to hydrolyze that in acid or in base, and in base what you're going to get is, basically you're going to form the acid in the mechanism, and then it's going to get deprotonated. Like there's just there's no way to like just form the anion, because we're not going to have O2 minus like just floating around by itself, right? So you're going to form the carboxylic acid and then deprotonate, and that deprotonation is what drives this reaction to completion. And then this guy is going to, if you're in base, require a workup with acid, aqueous acid, and then you can get, usually you're still going to get NH4Cl or something, because ammonia, I want to say ammonia is a gas. Yeah, I'm pretty sure NH3 is a gas, and NH4 plus, like, if you just have aqueous ammonium, or ammonia, if it says, ammonia is this, plus water gives you, I should have drawn that something else, whatever. And you get NH4 plus OH minus. So NH4OH. It's exactly the same thing. It's just if you've got ammonia and it's not a gas, so you've got water around, it's gonna look like this. NH4OH is just the version of putting, this isn't acidic because it's got a OH minus counter ion, so it's neutral. Yeah, does that make sense? So like, just whenever you form ammonium, ammonium hydroxide, which sounds like it's very basic, but doesn't actually have to be. acidify that, you're still going to have ammonium, but I guess ammonium chloride, and that's going to convert your carboxylate anion into the carboxylic acid that you wanted in the first place. Okay. If this is like significantly easier for you guys to see, you should remind me at the beginning of class. If it's just something that like eventually it bothers me because it glares in funny ways when I stand in specific areas, then we can just play the game where I eventually turn the light off after coming in from the outside and feeling like it's dark and turning it on. Nitriles, hydrolysis of nitriles is a really valuable way to synthesize carboxylic acids from primary or secondary haloalkanes, right? Because if we've got a primary or secondary haloalkane, so we've just got normal ass alkane and there's a chloride on there or another halogen, right? We can do KCN, so just cyanide ion, right, in ethanol and water, and we make a nitrile. And remember, yeah, I do not like the way that they've shown that here. So I'm gonna write this out, but it's gonna be short, I promise. Because the way that they drew that, you might not notice that right here there's an 8, and right here they changed it to a 9. That's just tricky and sneaky, and I don't like it. So if you're gonna draw me, if they are gonna draw me CH3, CH2, 8, CH2Cl, which is just, you know, a chlorine off of that, and they're gonna say plus KCN in ethanol and water, then they're going to show me the products like this: CH3, CH2, 8, CH2CN, right? Because this shows us what we did, right? This like demonstrates, oh, we didn't just change the chlorine to this color coding is not specifically electrophile, nucleophile right now. Just color coding for this. So we add a carbon when we do this, right? And we don't usually do that. Like a lot of times we have to very specifically like, oh, we added something to the carbonyl carbon. In this case, we're adding the carbonyl carbon, or the thing that's going to become a carbonyl carbon if we make it into a carbonyl, right? So this carbon gets added on with there. Side note, same with a Grignard reagent, GBr plus CO2, you're gonna get R, exactly that same R, and then that. Well, and then acid workup. Otherwise, if we don't have the acid workup, you'll just get that, but same thing. So we added a carbon. When we do CO2 and a Grignard reagent, we add a carbon in there. When we make a nitrile from a halide, a haloalkane, we're going to add a carbon. Yes, nitrogen brings its own carbon. BYOC. I have to entertain myself. I like to think I'm funny. It's all right if you don't, but I do appreciate the humor in you. All right. So, let's see. Hydrolysis of cyanohydrins. So we've done, that's a cyanohydrin, right? So cyanohydrin is just, we've got a CN on, well, basically we added a CN minus, right? CN minus attacked a carbonyl carbon, so now we've got addition to a, in this case, aldehyde. So we've got an alcohol right next to a nitrile. There's a hydrogen on here because there was a hydrogen here. Yes? So we just did addition. So if you make one of these, a cyanohydrin, you can hydrolyze that to make an alpha hydroxy carboxylic acid. So carboxylic acid with alpha. On the alpha carbon, you've got that. And again, COOH, so this CN, its own carbon, COOH. Same carbon turns into, from C triple bond to N to carboxylic acid. But that's not the carbon, that's the carbonyl carbon now, right? That's not the carbon that started as a carbonyl carbon, right? Because back here, this guy's the carbonyl carbon. And when we added CN minus, he just became a little intersection of lines, right? He's not a carbonyl carbon anymore, and he stays not a carbonyl carbon. We added CN minus, C triple bonded to N, and that's the one that became the new carbonyl carbon. Yes? Okay. I just, most of the time, we're just attacking the carbonyl carbon, and a lot of times we reform it right there, so I want to be really specific when we change the number of carbons happening.